Hey, what's good, my young ensemble? How about them horns? Horns for sure. Well, all right, so we're going to continue on in our discussion of waves. And I want to kind of share a story with you. Actually, when I was younger, I was in the Houston Youth Orchestra. I played viola. And the constructor would simply guide us through the music, cue us on when to play. So he'd instruct the violins. He'd say, "Violins, it's your turn to play." And so they'd start playing as he guided them. Nextly, if that's even a word, he'd instruct the violas to come in and start playing. And then he'd instruct the cellos and the bass. And I remember, you have to recall, uh, I was young at the time and I didn't understand. But whenever we'd play a little offbeat or something wasn't quite right, he'd always say, "Now, if you continue to do that, the crowd, they're going to throw tomatoes at me." And I thought to myself, wow, why is that the case? Why would they throw tomatoes at you? And ultimately, nowadays, I realize it's because the music would have sounded badly, you know? But uh, I'm only mentioning all of this because now we almost have the tools to be able to describe exactly what happens whenever two disturbances, two waves. Remember, I told you that sound is a wave at the beginning of the semester. Whenever there's two sounds playing at the same time, what happens? We're almost to the point where we're able to describe that. Okay, so uh, in today's lecture, we're going to begin to build that foundation of being able to describe this phenomena of when two vibrations, waves, whatever you want to call them, disturbances, occur at the same time. And actually, we're going to start with the simplest case. So you see here, I have lecture 4, superposition of periodic motion. So we're going to go back. Instead of describing sound waves, we're going to describe um, the mechanical waves. We're going to use the example of the mechanical waves that we're more comfortable with to build this foundation. Um, but we're going to start with the most simplest case. And that simple case is two waves of the same frequency. Okay, and so let's go ahead and start. Oh, but before I do start, let me say, like, comment, subscribe. Also, follow my Instagram channel for the hints and the discussions. All right, so let's go ahead and start though. So let's suppose we had two disturbances. All right, two disturbances. The first disturbance, we'll call it x1. Okay, x1 of t equal to, let's say it had some amplitude, a1 cosine omega t plus alpha. All right, that's an a. Let me make it clearer. A1 cosine omega t plus alpha 1, and x2 of t is a2 cosine omega t plus alpha 2. All right, so these two disturbances, these two waves, have the same frequency, different phases, but in different amplitudes. Okay, but they have the same frequency. Okay, um, that is the condition that we're discussing here. So the condition here we're talking about is same frequency. All right, there's going to be more discussion on what happens when we have different frequencies. But for now, let's build this foundation. And I want to take this very slowly. I don't want to I don't want to rush this. I think rushing through this idea could be very um, uh, troublesome in the future. So let's make sure we completely understand the simplest case to begin with. But I said that the thing that we're trying to describe is what happens when these two waves, these two disturbances occur at the same time. All right, and so what we will do is we'll make a guess. We'll guess what happens. Okay, um, we'll guess that the two waves add together. All right, and the adding of these two waves is what we call the superposition of the wave. And so that's just a fancy word that physicists use. You've probably heard it in your classical mechanics class. You've probably heard it in your, especially in your E&M class when you talk about the superposition of electric fields, right? What did you do? You just added two electric fields, all right? And so the same thing is going to occur here. When we're talking about the superposition of two waves, two disturbances, we're simply saying we're adding the two together. So, so the resulting wave is going to be this x of t is equal to a one. Well, let me take a step back. Maybe I'm going a little too fast. It's going to be x1t plus x2 of t, and that's just equal to a1 cosine omega t plus alpha 1 plus, that's a 1 here, a2 cosine omega t plus alpha 2. All right, and so that is what the resultant wave x of t, we're going to guess it would be, its description would be. Okay, now remember I told you that when we have the violins playing, and let's say a violin played, one of the violinists, they played some sound. Let's say they played a D note. All right, there's actually a D string. Okay, let's say they just plucked the D, or not even plucked it. Let's say they actually played the D note, and then another violinist, decided to join in and add another D note. Right? It's the same frequency. You hear the same sound. So what ends up happening? Those two sounds add together. That's what we're saying is occurring. That's how we're describing. The same thing would happen with these mechanical waves that we're describing. You're going to get a superposition of that sound. All right. But what did we notice about the resultant, right, of the resulting sound? It's the same note, right? It may be a little louder, it may be a little fainter, who knows? But it's the same note. So it's pretty safe to guess that our resultant x of t is going to be some amplitude. It's going to have some amplitude, and it's going to be some cosine omega is going to have the same frequency plus some phase alpha, and that's ultimately what will be the description of our resultant wave. And so this is what I want to actually box here. And so what are we going to discuss today? Today we're going to discuss how will we describe or how will we determine what our amplitude of this resultant wave is, and its phase alpha, using the information that we already know, using the fact that we know that x1 is composed of a1 cosine omega t plus alpha 1, and x2 is composed of a2 cosine omega t plus alpha 2. All right, that's what we want to do. That's what we're going to work on today. And so in order to do this, I'm going to use what is called the rotating vector representation of these waves. And if you want to read more on this rotating vector idea, please feel free to pick up your copy of AP French that I told you I'm lecturing out of. Um, the idea is pretty simple. Hopefully, as I'm going through it, maybe I can kind of explain the idea. But suppose we had some axis. All right, this could be our y-axis. It wouldn't matter what that axis is, but this is the only axis that would actually matter, and we'll make sure to label it. It's our x-axis, okay? And it's describing our x1, x2, where these x1 and x2 exist within our plane, okay? And let's say we had some vector, right? We said it's some rotating vector that made some angle with the x-axis, some vector that has some angle with the x-axis that is omega t plus alpha 1. Okay, hopefully that makes sense. Its length is a1. So this is our x1 vector. Okay, and hopefully this makes sense because what's going on here, let me go to my little laser. Hopefully it makes sense that if I were to project a1 onto the x-axis, how would I do that, right? I would just simply, well, I guess I shouldn't say projection, rather I should say if I wanted the x component of a1, what would I do? I'd take the cosine of the angle that it's making with the x-axis, right? And so that's why I'm saying that this vector here is representing our wave x1, which is x1, which is a1 cosine omega t plus alpha 1. All right, and we could do the same thing for x2. So a2 cosine omega t plus alpha 2. I just want to rewrite these things so that you can remember them. But, so now let's say this is our a2, and it's making some angle that is omega t plus alpha 2. Ooh, excuse me. And it's a length a2. All right, and I'm gonna move this so that I can get a little more space. I'm gonna need more space. So yeah, I'll just come to the new page. See, this is why it's so great to have this iPad, right? I'll just cut this and I'll put it up here. There we go. All right. Oops. Well, maybe I can put it on this page, make it look a little more decent in my presentation. All right. So now that we have these vectors written out, what will our resultant vector be? We said that it'd be the composition or the sum of the two vectors, right? It's the sum of the two waves. That's what we've postulated. So how do we add vectors? From your classical mechanics class, you probably remember, okay, if I just take this a2 vector, place it on the tip of a1, I could do the same thing with a1, right, to a2. Well, let me not do that yet. Maybe I'm skipping steps. My resultant vector is going to go from tip to tail, or tail to tip rather, of a1 to a2. That's what a1 plus a2 would look like in vector representation, in vector form, right? So this ultimately must be my vector A. And maybe it'd be better if I just change colors, actually. Let me Let me do that. That way there is not any confusion. So I'm going to make A2 my red vector. I could have made it orange, but oh well. So A2, this is A2. This is A1. I'll make A1 blue. What did I end up doing? I made this red. This is actually a lot of fun because now you get here. I'm just really kind of freestyling it. You're getting this chance to see that I don't have to necessarily have anything written out. I can just kind of go with the flow, you know? And that's part of physics. Okay, so there's my A2. You gotta be comfortable doing such a thing. And now my resultant, I'll use a different color. Actually, maybe I should move A2 over here. There we go. And my resultant can be black. I guess red and blue make purple. I could have done that, but I'll use black. So my resultant vector would be A. It's my A. Let's come over here. Let's change the colors, right? Let's make some angle omega t plus alpha 1. Feel free to, you know, 2 times speed this because I'm just simply representing all the information I've already stated. But that angle there is my omega t plus alpha 2. And lastly, so what is this angle that A is making with the x-axis? This angle is going to be some omega t plus alpha. All right. Hopefully that's clear. If not, then maybe ask about it in the comments and maybe I can explain it a little more. But for now, I'll continue on. So what is it that we're interested in finding? Well, we want to find what the length of this vector A is, right? And we're given this triangle A, A1 and A2. All right, that's the triangle we're given. So we need to, and we're also given angles. All right, so let me come over here and actually draw a line that's parallel to the x-axis, okay? Where the vectors A1 and A2 meet. That's parallel to the x-axis. So, and let's also extend our A1 vector, like it's not literally extended, but draw a line that is at the same angle to that axis as our A1. To where we know that this angle is some omega t plus alpha 1. And we know that this angle is some omega t, well, let me not put it there. Let me put it down here. We know that that angle is some omega t plus alpha 2, right? And if we're able to determine what this angle is, this angle we'll call it delta. If we're able to determine what this angle delta is, we can use the law of cosines to determine what the length of A is, right? So what would this angle delta be? So let's come over here and write out what delta would be. delta would equal, well, we know that this angle is omega t plus alpha 2, right? So it's going to be some omega t plus alpha 2. I guess I could write it in red, I don't care, just to stay a little consistent. It's going to be omega t plus alpha 2, and that's going to be minus this angle, right? This omega t plus alpha 1. And I'm going very slowly because I want everyone to be able to follow this. If I were presenting this to an audience of like undergraduate students at university, I'd probably go a lot faster. I might not even give them what this angle delta is. I'd probably ask them to determine it themselves. But because I don't know who my audience is, I feel like I should just go ahead and break this down. So what do we end up with? We have that this omega t plus alpha 2 minus an omega t. So the omega t's cancel, and it's minus alpha, right? This minus sign distributes through here. And so we just end up with some alpha 2 minus alpha 1. All right, hopefully that's clear. So we find that our angle delta is just equal to, well, I don't even have to put that there, alpha 2 minus alpha 1. All right. And using the law of cosines, and it is indeed the law of cosines, we'll find that a squared is equal to a1 squared plus a2 squared, and it's going to actually be plus because we're using this angle delta as opposed to this angle, I don't know, let's if we called it theta, all right? And because what? Plus this angle is equal to minus this angle. So the law of cosines is minus would actually be a1 squared plus a2 squared minus 2a1 blah, blah, blah cosine of this angle theta. But that angle is equal to minus the cosine of this angle. So you would end up with plus 2 a1 a2 cosine of delta, which is just equal to a1 squared plus a2 squared plus 2a1 a2 cosine of alpha 2 minus alpha 1. All right, and that's a1 squared. Oh, sorry, not a1 squared, but a squared. All right. So now we found what the length of A is. All right, we'll just take the square root of that, and we're only going to take the positive root of it. We're going to assume that the amplitude is positive. All right, so because why is that? We assume that the angle is positive, or rather not the angle, but the amplitude is positive, simply because if we wanted to represent some negative x of t, this cosine function goes through the values of positive, well, minus one, well, positive 1 and minus 1, right? And so if we needed to represent some negative x of t, we simply could just change whatever the phase within this cosine argument is to get to progress the cosine function to be that negative x of t that we were looking for. So for that reason, we only need to take the positive root of the amplitude. Okay, I hope that makes sense. And shout out to Professor Heinzen for instructing that, for teaching me that. So yes, so let me continue. So now we've already related what the amplitude is. Now we need to determine, what was the last thing we needed to determine? We need to determine what alpha is, okay? Now that we have A, what is alpha? So how do we find what alpha is? You know, I could give you a concept quiz on how to do that and have you determine that yourself. However, I'll actually do it for you here. So, because I realized geometry is actually very difficult. Geometry is not one of the easiest topics. And that's another reason I wanted to take this lecture very slowly. It's a very difficult thing to do, and if you're not familiar with doing it or performing these things, it's always good to see someone before you do it, and then you can, one, copy what they've done, and then two, progress and further it for yourself. Right. So uh, that's why I'm actually doing this, and that's why I'm taking this one super slowly, and I won't continue into the description of uh, two, what happens when you add two disturbances of different frequencies on today's lecture. Uh, so now, all right, let's go back to here. Let's go back to our graph, and actually let me draw A1 up here, because now we're trying to find out what alpha is, right? So I've drawn my A1. This is my A1. And what you really want to notice, this is going to look like a very sloppy graph, all right? But just try and make out what you can, whatever it is you can. But notice over here that this A2 to A1, that's that angle delta, right? That's our angle delta. Actually, you know what? Let me use the same color, because I've already given it a color. Why not use the same one? That's our angle delta. All right. So let's call. Let's see. Let's call, and we know that this is angle omega t plus alpha, right? So let's call this angle here between A and A1. Let's call that angle, I don't know, let's give it some green. Let's call that some angle. I'm going to call it beta. Let's call it beta. So what must beta be? Beta is going to equal our what is beta going to equal, actually? That's a good question. Oh, beta's going to equal, I know. Beta is going to equal our omega t plus alpha minus omega t plus alpha 1. All right. So, even see, this is another reason we're going slowly on this one. It takes some time to actually get this stuff. It's not very simple to see. Geometry is a very difficult subject. So our angle beta is going to equal, I'll put it in black. Beta is going to equal that omega t plus alpha, and it's minus our omega t plus alpha 1. And what do we end up with? Well, minus sign distributes again, minus that, and we get beta is equal to our alpha minus alpha 1. So if we want what alpha is, if we want alpha, or beta, alpha. If we want alpha, alpha is just going to be our beta plus alpha 1. So we need to determine what this angle beta is. And I hope it's pretty clear to see from this graph. That A splits this parallelogram. A splits this parallelogram that's composed of A2, A2, and A1, right? It splits this. So whatever this angle beta is, it must be half the angle of delta. I hope that's clear. Like, it would take two betas. Maybe I should draw it over here to make it even more clear. But it would take two betas to make one delta, right? It would take two betas to make one delta. So I hope that's pretty clear. So we can see here that that beta must be equal to, let me write it over here to be explicit, and maybe I should even use green. But beta should be equal to, what did I say? Delta. I'll use orange, trying to stay consistent. It's very difficult. Delta divided by 2. I really hate all the changing colors, so from now on, I'm just gonna write black. All right, but uh yeah, I don't like that. But beta is just equal to delta divided by 2. All right. I'm done using different colors. All right. Hopefully, it's just clear to you at this point. Maybe and you don't need the colors to associate with the angles. But now that we know that that's what beta is, well, what was delta? Delta was alpha 2 minus alpha 1. So beta is going to be alpha 2 minus alpha 1 divided by 2, uh, right? And then now, if we want to find out what alpha is this beta. So this is alpha 2 minus alpha 1 divided by 2 plus alpha 1. Well, what does that equal to? That's just alpha. This is just, I'll write it out because I don't want to, lose anyone. Alpha 1 over 2 plus 2 alpha 1 over 2, right? I just multiplied by 1. And you add this together. 2 minus 1 is a 1. So then you just end up with what? You just end up with alpha is equal to alpha 2 minus alpha 1 divided by 2. Or rather, plus. See, I even mess up sometimes. It's plus. All right. And that is what you would do to find alpha. So that's the value of our alpha. So you see for I guess I could even try to write it out. I'm not going to write that whole expression out, but let's just quickly recap. We found that a squared is equal to a1 squared plus a2 squared plus 2a1 a2 cosine of alpha 2 minus alpha 1. So we related how the amplitude is related to the two things that we, or the four things that we knew, the amplitude of our first disturbance and the amplitude of our second disturbance, as well as the phases of our disturbances. It's actually related to the phase difference between our disturbances, right? Um, and lastly, what else did we find? We found that alpha is equal to uh, the sum, or the average rather, the average of our two phase differences. All right. So that's what that would be the characteristics of our resultant x of t, which is that a cosine omega t, it has the same frequency plus alpha. All right. And so notice everything that we discussed here, it was really mostly math. The only physics in this was actually the discussion of the superposition of the waves, how we actually got this resultant wave. That was really the only physics that we've really discussed during this lecture. However, you know, math is really important to physics, and this course in particular is a jump up. I know last time we talked about complex variables, right? And so you have to get very familiar, very comfortable with the language that we use to describe these natural phenomena within physics, okay? And so, in order to gain a little more comfortability, I want you to show this relation. This relation that I have boxed here, I want you to show, and I'll write it out. I'll write it out in red. Show that a squared is equal to a1 squared plus a2 squared plus 2a1 a2 cosine alpha 2 minus alpha 1 using complex exponentials. Using the complex exponentials. Form of the disturbances. So what am I saying? I'm saying I want you to use the fact that x1 of t is equal to a1 e to the I omega t plus alpha 1, and that x2 is equal to a2 e to the I omega t plus alpha 2. Oh, and let me be a little more precise here. X2 of t. Go back here. X2 of t. There you go. All right. So that's everything for today. I know we didn't cover very much, and it was a very slow lecture. However, I feel that this was a pretty difficult one. It's going to be very difficult for people to follow, especially if it's your first time doing this. So um, I know they cover it in the book. They don't necessarily show you all of the steps that I've showed you, but this exercise is going to give you a little more familiarity with complex exponentials. And I'm debating whether or not I want to share a hint with you on this one. Um, actually, no, I don't think I'm gonna give you a hint for this one. But you can look at the Instagram to, you know, if you need any assistance. So yeah, that's everything. Um, and once again, remember, like, comment, subscribe, follow my Instagram at Lord Claiborne, Lord_Claiborne. It'll be in the description below. And remember, all right, I'm gonna teach it to you again. When I say how about them horns, you say horns for sure. So yes, sir. All right, y'all are my young ensemble. If you want to join the ensemble, subscribe, baby. Subscribe and join the ensemble. So I'll catch y'all later, and hook 'em horns.